A couple of the other forms that we're going to tackle with L'Hopital's rule. So far, the ones that we've done 0 over 0, and then we've done infinity over infinity. And those are hopefully fairly straightforward in the homework last night, I'm hoping. So, if you did it. But anyways, those are the two main indeterminate forms. A couple others pop up, and there's a couple tricks with those that I'll show you and explain and whatnot. A couple of the other forms are 0 multiplied by infinity. That's one of the big ones that'll pop up. That's an easy fix one, though. That 0 over infinity is usually an easy fix one. 0 to the 0 power is a weird one. Infinity to the 0 power is a weird one. See, we assume a lot of that stuff. It's not always true. Let's see. 1 to the infinity power. So some weird things pop up like this. I'll show you ways to fix. We can categorize. Oh, and the last one is infinity minus infinity. And we can kind of group these together. Usually these three right here fit pretty well with each other. They're going to, like as far as how to solve a problem, those three are going to be the same style. These three right here are going to be the same style right here, and then that infinity minus infinity is kind of on its own. It's its own issue, its own entity. So let's first start with, let's start with this one, 0 times infinity. We'll try to figure out a form that goes like that. So if we did the limit as x went to infinity, we did kind of one like this yesterday, but e to the negative x times the square root of x. Now the first part, the e to the negative x, that's, if I plug in an infinity there, that would be, well, negative infinity, and e to the negative infinity would be 1 over e to the infinity. So 1 over a really, really big number is going to go to 0. So this number is going to go towards 0. And then if I plug infinity in here, it's going to go towards infinity. So the form for this one is 0 times infinity. Now a way to fix that, a way to get to L'Hopital's rule, we need to have one of those two forms in order to use L'Hopital's rule. So we have to fix this, we have to adjust this so that it looks like one of those two right there. So all we do is we move one or the other. We move the 0, we move the infinity term, and move it to the other side of the fraction sign and see if that fixes our issue. So for example, like this e to the negative x, if I just bump that down to the bottom, it would be the square root of x divided by e to the positive x of the limit as x goes to infinity. And now I've changed the form. I've changed just the form factor of how it's going to fit. Now I can use L'Hopital's rule on this one, because if I plug infinity on the numerator, it's infinity. Plug infinity on the denominator, e to the infinity power is going to go towards infinity. So it's going to go with that value. Now it works. Now you can use L'Hopital's rule real quick and hopefully it works out for you. So I take the derivative of the numerator, derivative of the denominator. Hopefully we get a decent answer. So derivative of the square root of x is 1 over 2 square roots of x divided by e to the x.
Isn't the square root of x on the bottom?
It is. I wrote that. If that's right, maybe I'll do this. I'll do this.
Oh, okay.
There we go. That'll fix it. Those side fractions confuse people sometimes. I don't write very often. What's that?
What would that mean simplified?
What would this mean simplified? E to the x would be on the top then on this. No. It'd be on the bottom still.
2 e to the x.
It'd be 1 over 2 e to the x squared of x if you wanted to simplify it. Now, simplifying this one's a bit overkill. We don't need to. Because if we plug in an infinity, right, look at what the numerator is going to go to. Right? What's the numerator going to go to?
0.
It's going to go to 0, right? So now we have 0 divided by infinity. 0. 0 divided by anything, any number, is going to go to infinity.
Wouldn't 0 times infinity already equal 0?
You would think so.
Why?
But not always, unfortunately. Not always.
How does it not equal?
I'll show you. I know. There's some lame ones.
Why would they tell us this in like elementary school only to tell us it's all a lie?
It's all a lie.
Everything you learned is a lie. Except baseball.
Here's my counterexample for why it doesn't always work, or one of the counters. There's a couple counterexamples.
Which one would be going to infinity?
You would think this one would go to infinity. But unfortunately, this one actually doesn't go to infinity. What's this one go to? 2. Goes to 2. Why does it go to 2? Because the x is canceled, exactly. But the form for this, if I plugged in a 0, right, this would be 0. If I plug the 0 in here, 2 over 0 goes to infinity. So it's 0 times something that goes to infinity, which is kind of a weird concept, but those zeros in essence are going to cancel each other out. We might have a hole at certain spots, but eventually in the long run, as we get closer and closer to 0, our value there is going to get to 2. So it's not always 0 times something is going to equal 0, unfortunately. I know it's brutal. If you want to, you can change this form factor a little bit to make that an infinity over infinity or 0 over 0, and use L'Hopital's rule. And you know, when you do all that stuff, you still get 2 in the long run. But way easier to see that the x's cancel and life is good. So, anyways, so that's one thing to watch out for. But typically, you just move 1 to the other side. So that's the forms that are going to fall into this category here. You just force it into one of those, and then life is good. Okay, now the new stuff for today mostly is going to be dealt with these 3 concepts right here, 0 to 0, infinity to 0, 1 to 0. Those are the big ones that the new trick is going to be involved today. That one you just can move to the other side.
What if it's e to the infinity?
E to the infinity goes to infinity.
Well, because you have the 1 to infinity, so it's 1.
Right, but 1 to...
0.
But E is a different number other than 1. E is not an identity number.
E to the 0, that's 1.
E to the 0 is 1.
You rate it.
Because those are both specific numbers. E to the 0 is 1.
So, yeah.
What did you say? 1 to the infinity is not always 1.
What?
I know.
Why?
Another one. I know.
Alright, prove that.
I will.
Alright, so according to that, 2 divided by 0 is infinity.
Say it again.
According to that, 2 divided by 0 is infinity.
Correct.
Undefined.
Well, we can't actually divide by 0, right? But if I plug a number in really, really close to 0, like 0.000001, right? 2 divided by a tiny, tiny, tiny number is going to make it really big.
Right.
Okay. So that's going to eventually go towards infinity. So, anyways, the real tricky ones that are kind of tough pills to swallow are some of these right here. Infinity to 0, 1 to the infinity, and 0 to 0. Those are kind of the odd ones to do. How to do them, they're actually not too bad as far as how to solve them, at least the ideas of them. Let me throw one down here. This one would be a limit as x goes to infinity. See, the tough part about these is you're thinking of infinity as a specific number, and it's an idea, it's a concept. And that's kind of a tough pill to swallow, because all those rules that you learned when you were a kid were all for specific numbers. They were all for a certain number. But with infinity, it's a little bit out there, you know? It's a concept. So,
Pretty sure we're learning how to
I've done with that.
We're learning how to open black holes.
Yeah.
Like imaginary numbers.
We're getting there. The world will blow up. The world will blow up. So, anyways, this function right here, this function is y. So really, this is going to be y equals the limit as x goes to infinity of 1 plus 1 over x to the x. Now, if I plugged in this infinity right here, let's just see what that power would go to. What form would it be in? What indeterminate form is it? That's what I want to know.
Infinity to the infinity. Oh, 0 to the
1 to the infinity. This is a 1 to the infinity style problem, hopefully, okay? Because if I plug an infinity there, that goes to 0. So I've got 1 plus 0 raised to the infinity power. So I have 1 to the infinity power. We're all thinking that it's 1. And it's not.
Why?
Anyways,
No.
so to do this problem, there's not a specific form that we're looking for. But since we have this exponent right here, the way to fix that is to use natural logs. Okay, if we use natural logs with an exponent, I can move that exponent into the front, and then I can hopefully simplify a little further. So what I'm going to do is I'm going to take the natural log of both sides. I'm going to say the natural log of y, and it's going to be the natural log of this limit, whatever this function is. So I've got the natural log of y equals the natural log of this limit of stuff. Since this is a continuous function, since it's a nice thing for us to do, and all of tonight's will be continuous. But we can do the limit as x goes to infinity of the natural log of 1 plus 1 over x to the x power. X just goes in the front. Okay, so that x bumps into the front right there, being that it's the exponent of the logarithm. So that bumps to the front. That's good. Now maybe I can plug in that infinity. Maybe I can see what would happen if I just straight plugged in that infinity. Well, if I plugged in infinity here into that x, that would give me infinity. Multiplied by, if I plugged in infinity here, what would that give me?
1.
But what's
The quantity?
Yeah, with the natural log of 1 plus 1 over x.
Is that 0?
It'd be 0. It'd be 0. Okay, it'd be ln of 1, all right? Natural log of 1, any log of 1 is going to go to 0. So I've got this infinity times 0 thing again that I have to fix. I have to try to change that. In order to use L'Hopital's rule, it's got to be 0 over 0 or infinity over infinity, one of those two. So I'm going to tweak this just a little bit. I still got my limit as x goes to infinity. And I've got this x right here. This is my infinity part. If I put this on the denominator, it would turn into 1 over x on the denominator. Following that? Kind of? Instead of multiplying by x, I'm going to divide by its reciprocal. Might be a better way to say that. My numerator is the same. It's natural log of 1 plus 1 over x. Now I have a good form that I can use L'Hopital's rule with to try to make this a little bit easier of a problem, hopefully. Okay. So we got L'Hopital's rule. So let's see, if I plugged in an infinity here, it'd be, this goes away. Natural log of 1 is 0. So now I'm at the 0 over plug in infinity, I'm at 0. So now I'm 0 over 0. Okay, L'Hopital's rule, we can do it now. Okay, so take the derivative of the numerator and the denominator and see what you get. Derivative of the natural log, we got to do that to u prime over u, right? So we got to take the derivative of the inside, which is going to be negative 1 over x squared, I think. I hope. Maybe. Multiplied by, or I guess I should say divided by.
Oh.
Right. Fine, I'll write the divided. All right, I'll write it this way. Divided by, I'll go side divide, which I don't like that much, but divided by the denominator, or divided by u, which was the 1 plus 1 over x. So 1 plus 1 over x, that's all in that denominator. Now this is divided by, that's the numerator, right? That's just the derivative of the natural log, right? Divided by the derivative of 1 over x.
Can we, those two go away?
They do.
Magical.
Isn't that nice? Yeah, it's a little tricky with the go away part here. It's not that actually you can actually cheat here and actually be okay. But these two cancel. Yes, those two cancel, so you're okay with that. And then I've got, what's left is I've still got this fraction I'm going to worry about. I've got a 1 left on the top, so it's 1 over this part right here. So it's 1 over 1 plus 1 over x. So that's what's left over. But now I can plug in my infinity. Right now I'm not in an indeterminate form. I can just straight substitute, which you guys are really not going to like. But I plug in an infinity right there. 1 over infinity is 0. So this bottom denominator is 1. So I get 1 over 1, which is 1.
How does that not equal?
No, how does that not equal 1? I know. How does that not equal 1?
Wait, didn't we just...
Wait, why is it 1?
The natural log of y equals 1. Okay?
No.
The function doesn't equal
No.
1. The natural log of y doesn't equal. That's what equals 1. I know, crazy, huh? So really we have the natural log of y equals 1, which one little extra step here. But the limit for this guy is, if I were to solve for y, let's say, is e to the first.
So it's e.
So it's e.
2.1897.
2.718281828.
What?
Awesome. I know, so it's not 1. I know, you're right. All right, now my saving grace for this is my saving grace. If you were to take this function right here, that was my original function. If you were to graph that and you started plugging in really big numbers, if you looked at the characteristics of that graph, at the very, very far right side, just plugged in infinity, your y values would end up getting really, really close to 2.7. So that's my only saving grace here, is that if you were to graph that, it will verify my craziness.
Which guy?
My psycho. But graphing is good. So, anyways, let's try it. Let's mess around with one more of those real quick and see if we can.
So 1 of the infinity doesn't equal 1.
It depends on the function. See that one of the infinity power, that was just the form for what that's going to be. Now that might turn into something else. All that does is tell you to use logarithms for how to solve it. That's all you're going to do. The 1 to infinity power, that's not a specific number. That's a concept still. So we don't want to generalize that to a specific number yet. So, anyways, it's kind of like we can't generalize this to 0. I showed you one where it equals 2. I can show you one where it equals 3, 4, 5, whatever. I can make up whatever I want. Make that not equal 0. So. Anyways, let's try one of these other forms right here. Let's do the limit as x goes to, let's go to 0 on this one. And let's have sine of x to the x.
So 0 to the 0.
It's a 0 to the 0 one. Now you guys are probably a little happier not saying that that's either 0 or 1, right? You guys would probably argue all day on what 0 to the 0 power
Can
would
it
equal.
just be like,
0.
no, maybe we can compromise
Oh,
and make
anybody
people
do
point
0?
that.
It could equal 3 considering this function. You're right. It could equal 3. But if I were to plug in a 0, I get sine of 0, which is 0, and raised to the 0 power. So my form here is 0 to the 0. Anytime I have this power-ish idea, this concept, natural logs are what I want to do. So I would say the natural log of y, considering this is all a function of y, equals the natural log. I'm going to write the limit first. We can jump that step, right? Limit as x goes to 0 of the natural log of sine of x raised to the x power. Okay, bump the x in the front. Yep, bump the x in the front. See what form it's in. Plug it in a 0 right there. Let's see, it's 0. Ooh, this one's going to be a funny one. Natural log of 0. What's the natural log of 0?
Must be infinity.
Must be infinity. Must be infinity.
Why? Magical.
Why is that infinity?
What's the natural log of 0 on your calculator? Domain error, right? It yells at you, right? Because you can't ever take the natural log of that. But you plug in a number really, really close to 0. Like 0.000001 and see what you get. The natural log of that.
0.
Oh, it gives you 0?
Oh, I did 0. Never mind.
It's
the same number. I didn't put the why.
Anyways, it's going to give you a funny form, right?
Negative 29 point. I'll do like a bazillion.
Anyways, it's going to be a bad form. So we need to change, we need to tweak this just a
I'll
little
make it
bit.
negative 96.
Okay, so I would first take this x right here, put that 0 in the bottom, right? So we're going to have the natural log of sine of x, and then divided by 1 divided by x. That moves the 0 part to the bottom. It's going to give me an infinity over infinity. So now I can use L'Hopital's rule.
Oh.
It's throwing me off running limits and LNs.
Say it again.
It's throwing me off running limits and LNs at the same time.
Oh, limits and lns at the same time.
Almost the same time.
I'm not trying to confuse you. Well, yeah, kind of. It's fun. Math gods hate you right now. Right.
I have it made in a stack of.
All right, so apply the Lope.
I think they're calling it
Call.
L
L-hop.
This is gangster, man.
It's a local house of pancakes. So, sorry, man. Sorry, my bad. So, natural log of sine of x, take derivative of that u prime over u, right? So u prime, let's see, u prime derivative of sine would be cosine. So this would be cosine over sine. So this would be cotangent of x. Would be the derivative of natural log of sine of x.
Why?
Oh, sorry. Because this would be u prime over u, so u prime is cosine of x divided by u is sine of x. So I just cheated and did one step for cotangent. And then derivative of this is going to be, let's see, negative 1 over x squared, something like that. And this is kind of a funky deal. So I'm gonna equal this. Just gonna change this a little bit. Flip over this fraction. That will put a tangent of x on the bottom. Just might make it a little easier in a second. And then flip that one over, put it on the top, be a negative here, and then I got an x squared. And that equals, after L'Hopital's rule, will equal this. Now I'm taking the limit as x goes to 0, which I still have an issue here. I still have a problem. If I plug a 0 in here, it's 0. If I plug a 0 in there, tangent of 0 is 0, right? So I've got a 0 over 0 again. So that's okay. I'll just use L'Hopital's rule again here and see what you get. Okay, so L'Hopital's rule again. So I get a negative 2x for the top. Bottom derivative of tangent is
C squared.
secant squared. Ooh, so now I get what? I get 0 over what? 1. Good. Back to 0.
Now we have the ln of y.
So now we have the natural log of y equals 0. That's what all that equals. Quick little convert to find out what your limit's going to equal. 1. So that actually almost confirmed some people's guesses on the 0 to the 0 power.
Is that always it?
No.
It varies on the.
It varies on the problem.
God,
Varies
who
on the
invented this stupid
I know. One last one, and we're done.
L'Hopital, I swear.
L'Hopital.
Take him up and
So ironic.
It's hard to take in.
Now you know why they died when they were like 50. People murdered them.
Why did you unleash this upon the world? Our children will be suffering for the rest of their lives.
Okay, I just remember those.
Whoa.
Yeah, because, most time they don't really matter. Because you're going to manipulate anyways. To make it work so that you can't just plug a 1.
This is
You are cool.
this has to be the blue one left.
Stop that!
This is infinity minus infinity.
Not a single source of transmat. No water is not that. No, not okay.
So infinity minus infinity on this one. This one's actually not too bad.
How did you infinity minus infinity?
Because if I plug a 1 in there, natural 1, 0, 1 over something close to 0 is infinity.
Isn't that
1,
just didn't do
0,
that?
close to 0. What's that?
Isn't that 0?
Isn't what 0? Natural log of 1 is 0.
No.
You're right.
Infinity minus infinity.
Oh, but infinity is a concept, not a specific number.
So it's like infinity minus
Think about it this way. Maybe I think about it this way. Infinity 1, infinity 2.
Wouldn't that just equal infinity 3?
I'm just saying they don't have to be the same. That's all I'm saying. That's all I'm saying. It's a number. It's a concept.
Equals 2.
Alright.
And you know T stands for triangle, putting in solving this one.
Make it infinity.
Oh, man.
Put that in.
I like how these not one.
You should do it like infinity plus 1.
Infinity plus 1. Yeah, that's a good thing.
We should have a course in elementary school that dispels all of our hatred towards the class because of what they told us.
That would be good. On these ones, actually, all you have to do is add those together. Just common denominator of those. And then you'll have some kind of fraction where you might get an issue. So it's really not going to be too bad. It ends up being, x minus 1 minus the natural log of x, and then divide this by the natural log of x minus 1. Nope. That is just a common denominator. That's all that works.
What's the plus have to do with?
It just means it's coming from the positive side of 1. So if you were to plug in numbers on your calculator, like when I say close to 1, you could pick either, you're close to 1 right here, it'd be 1.0001 or 0.99999. So both those are really close to 1, but we're coming from the positive side. That's the only thing it does. So anyways, if I were to plug a 1 in here, let's see, what do I get? I get 1 here, this would be 0, minus natural log of 1 would be 0. So I get a 0 on the top, and then plugging a 1 there, that's 0 times
Magical.
0, which is 0. Okay, so it's 0 over 0. So now I can use L'Hopital's rule. There's no S. So I take the derivative of both of those guys. It's a little bit of work, but it's 1 minus 1 over x.
How are we supposed to take the derivative of this?
Product rule.
Oh, that was like last year.
So the derivative of this times that, so it's going to be x minus 1 times the derivative of that, which was 1 over x, plus natural log of x times the derivative of that, which is 1, so it's just going to be natural log of x. Now I got these 1 over x things. Let's just get rid of all of them, huh? Multiply everything by an x. Multiply everything by an x. So it'd be x minus 1 divided by x minus 1 and then plus x natural log of x.
Okay, what happened?
Multiply everything by an x.
Oh,
Actually, x over x. I lied. Multiply every term by an x. What I meant to say. I still can't plug in a 1 because then it would give me 0 over 0 still, right? So I actually have to use L'Hopital's rule there again, which is fine. No big deal. So take the derivative of both of those guys. So L'Hopital's rule there would be 1 divided by, derivative of this is 1. Is it 0? Is the answer 0?
okay.
I don't know either. We'll find out it's 1. Ooh, I'd like that if it were 1. And then I got a product rule this.
No.
Right?
Never mind.
Yeah, X natural. Well, do you have to product rule?
It's not even that
Yeah,
hard.
you
It's not
do.
even that hard.
Yeah, you have to product rule. Sorry.
ln of x equals.
So it'd be plus ln of x plus. So what I do, a derivative of this times this, and then plus.
X over X.
X over X.
Oh, plus 1.
Whoa.
Is that right? So it's just 1?
Yeah.
Yes, 1/2.
Jackpot.
Oh. So infinity minus infinity is 1/2.
I really like this class. I really like this.
In all seriousness, though, you still talking about